And lastly, we come to my favorite linear algebra application of them all, and that is social networks. Actually, what we're going to learn about in this segment applies to any kind of network. It doesn't have to be a social network, but that's what I'm doing research in these days and what I find particularly fascinating. When I say network, what I mean is a graph in the All the Math Volume 1, Episode 5 sense. So if you took All the Math Volume 1, you'll remember we have a data structure that is called a graph, which is composed of nodes and edges, and I'll draw one in a minute. But the idea is that many things in our increasingly internetworked world can be represented as a graph. And that's simply because the world is ultimately composed of things, and those things have relationships to other things. And that's essentially what we're modeling with any kind of graph. Notice this is a different kind of graph than the term you may have learned, and I'm sure you did learn in elementary school, where it's like an XY axis plot, right? That's not what we mean by graph. What we mean by graph is a set of nodes and edges. So let me draw one. We could say there's a bunch of computers, and each computer is connected to certain other computers on some sort of network. We might draw it like this. And this is indicating which of the nodes are connected to which other nodes. And we call that thing a node, also sometimes a vertex. Those are synonymous terms. And we call this thing here an edge, or sometimes we call it a link. That's a synonymous term. When two vertices are connected together, we call them adjacent. That means that they have an edge between them. There's several variations on graphs, which we'll look at. One is some graphs, the edges simply look like this. Others, the edges have arrowheads on them to indicate a direction. And maybe some of them have arrowheads on both sides, showing that the path goes in both directions. And that's because in some kinds of graphs, it makes sense to say that every single edge is inherently bidirectional. Okay, so like on Facebook, that's that way. If you're friends with somebody else, then they're automatically also friends with you. Friendship is inherently bidirectional. Therefore, you would use an undirected graph to represent Facebook, where the edges do not have arrowheads. On the other hand, something like Twitter, where you can follow someone without them necessarily following you back, you have to use a directed graph, which does have the arrowheads here. Okay, so we'll look at both in this little segment. And in fact, there's an interesting relation to matrices. A couple more things. So let me put our terms up here that we've learned. So we've learned the term undirected versus directed. That has to do with the presence of arrowheads or not. Another thing that is very common to do in graphs is to have like a number here on the edges, like maybe that's 10, and this is 15, and this is 7, and this is 8, and this is 3, and this is 2, and this is 1, and this is 9. Okay, if you have numbers like that, it's called a weighted graph. And that is useful if there's some sort of distance or cost between the nodes, right? Like maybe you say that this is the driving distance between two cities, or maybe you say this is the strength of the friendship between two people, or something like that. We would call it weighted, all right? Another term that we'll use in this little segment is the term degree. So when we talk about the degree of a vertex, we simply mean how many other vertices it is adjacent to. So when we're dealing with an undirected graph, if there are no arrowheads, then basically it's just how many lines are coming out of the thing. Okay, so in that case, the degree of this vertex here would be 3, because it's connected to 3 other vertices. And the degree of this one here would be 1, because it's only connected to 1 other vertex. And you can also have something called an isolate, which is a vertex that has no friends, which is kind of sad, but some vertices are kind of introverted like that. So that's what we call an degree. Now, a degree. Now, when we're dealing with a directed graph, we will use the terms in degree and out degree. And as you can probably guess, that just refers to how many incoming arrows there are and how many outgoing arrows there are. So in that case, we would say, let me finish all my arrowheads here. Let's say we have one there. Oops, let me put that in blue. And let's say we have one here. Then we would say that the in degree of that node right there is 2, because there's 2 incoming arrows. And then the out degree of this one would also be 2, coincidentally, because that's 2 outgoing arrows. Okay? And then just one more graph term, and then we'll get to the linear algebra stuff, is the word connected. And when we say a graph is connected, what we mean is that every vertex is reachable from every other vertex. So it's easier to see if you have an undirected graph. But let me draw another one down here. So if I have this graph here, and that connects to there, 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 and those two are connected. I shouldn't say connected. Those are adjacent, right? So these two nodes here are adjacent, and then we have these three all adjacent to each other, and then this one here adjacent to this. We would call this a non or a disconnected graph because you can't get to these guys up here from these ones down here and vice versa. If we added this edge here, it would still be not connected. But if we add this edge here, then suddenly it is connected because now it's possible to travel from one all the way to the others, right? So those are some basic graph terms. And that's review for you if you took all the math, Volume 1, Episode 5. Now, let's talk about linear algebra. So it turns out that there's many powerful things, and man, they are mind-blowing. Many of them we're not going to be able to do until we get to eigenvalues in a couple episodes. Okay, so I've mentioned eigenvalues a couple times, and they are this amazing thing about matrices that really sort of probe the inner intrinsic structure and reveal certain properties of it. But we can still get a lot of mileage out of simply using our matrix operations that we already know, and we're going to do something called an adjacency matrix. So remember I said that two vertices are adjacent if they have an edge between them, right? Two nodes are adjacent if they have a link between them. So to represent a graph, really you can do that in terms of a matrix, which is basically a list of all of the edges or lack thereof between all of the pairs of vertices. So let's look at what one looks like. Let's make a graph here again. I'm going to give this one 5 nodes, and I'm going to label them just so we can kind of work with this thing here. So there's A, B, C, D, and E. And I'm going to say that this is a directed graph. So I'm going to put some things on it like this, and I'm going to say those go in both directions, and you can get from B to C and from C to B. You can get from C to E and not vice versa. You can get from B to E and not vice versa. You can get from D to E. And then we're going to say that you can go from A to C. Okay. Now, the thing about a graph is that the only thing that really matters about it is not whether I made my arrows curvy or straight, not the fact that I put A in the upper left-hand corner visually and E in the bottom right-hand corner visually. None of those things really matter to what the graph is. All that matters is what are the vertices and which ones are connected by edges. And so what we're going to do is we're going to make a matrix called the adjacency matrix. Usually we call it A. This A just is referring to this matrix. It's not referring to this node A, so that's a different thing here. Maybe I'll call it ADJ just to kind of clarify that. And here's what we're going to do. We're going to say let's make the columns represent A, B, C, D, and E, and let's make the rows represent A, B, C, D, and E. An adjacency matrix is always square. And what we're going to do is we're simply going to put a 1 or a 0 based on whether there's an edge there or not. So A can go from A to B and also to C, but it can go nowhere else directly. So if we're standing on A and we want to follow the arrowed paths, we can go to C or B and nothing else. And that's why the top row of this adjacency matrix is going to look like this. We can go from A to B, we can go from A to C, but the other 3 vertices, I'm not able to traverse that way, and therefore it is, those have zeros there. So this axis, if you will, is the from, and this one here represents the to. And we can fill in the rest of the adjacency matrix like this, 1, 0, 1, 0, 1, indicating that I can go from B to A, C, and E. Verify that that's true in your mind. C is going to be 0, 1, 0, 0, 1, and D is going to be 1, 0, 0, 0, 1, and E is going to be all zeros, because you can't go anywhere from E according to this graph. It's a sink, is what that's called. Think of it as like a sinkhole. There's lots of stuff coming in, nothing coming out. Notice also that D has a completely zeroed column, and that's because nothing can go to D. D is purely a source vertex. You can't get into D from anywhere else, okay? So this thing's called an adjacency matrix, and it's pretty obvious how you would generalize this to a weighted graph, right? If there was a weighted graph, and I had numbers on this thing, like 4 and 3 and 2 and 6, I would simply put their number in this matrix instead of just putting a 1 or a 0. And by the way, if there were some zeros where basically I couldn't get from one place to another, then typically they would represent that as an infinity. So here I'd say you can't get from C to A directly, so that's essentially a distance of infinity to go from C to A. On the other hand, from C to E is only 5 units long, and so CE, we'd replace this with a 5. And then from C to B is 4 units long according to this, so C to B would be replaced by 4. And then we replace all of the zeros by infinities, because that would indicate that you can't travel along that path, right? All right, so that's an adjacency matrix, and hopefully it's clear that every single important thing about the graph is captured in the adjacency matrix. So if I showed you a graph and then I took it away, and all you could remember was the adjacency matrix, you could reconstruct the graph. You wouldn't draw it exactly the same, most likely, because you'd put the nodes in different places, because the position doesn't really matter anyway. But the adjacency matrix itself captures all the important information about a graph. Okay? Now, let's think about some of the properties of matrices that we've learned about, some of the special matrices, and I want to see if you can figure out how those correspond to the graph world here, right? So suppose I told you that I had an adjacency matrix here, and it had a bunch of entries. And what if I told you, and you looked at this and could verify, that the matrix is symmetric? What would that tell you about the graph it represents? Take a moment and see if you can figure that out. What if the matrix is symmetric? What does that tell you about the graph? And what you'll realize when you think it through is that the graph is, in that case, undirected. Now, why is there this relationship between a symmetric adjacency matrix and an undirected graph? The answer is simple. Symmetric matrix means that A at row I, column J is going to always be equal to A at row J, column I, right? So A2, 5 is going to always be equal to A5, 2 if it's a symmetric matrix. Put another way, it's reflexive along that diagonal, right? So if this guy up here is a 4, then this one here is going to be a 4. And this one here is a 7, that's going to be a 7. And up here in the corner, if that's a 9, that's going to be a 9, right? And if we're dealing with just ones and zeros, let's say we have a non-weighted graph, then that simply means that everywhere we have a 1 above the diagonal, we're going to have a 1 in the corresponding place reflected along the diagonal. So if this goes 1, 1, 1, 0, 1, then this is going to go 1, 1, 1, 0, 1. And if this goes 1, 0, 0, 0, then this is going to go 1, 0, 0, 0. That's what's going to be the case if we have a symmetric matrix. And the reason that goes with an undirected graph is because, in that case, the presence of an edge from vertex number A to vertex number B implies that there's also an edge between vertex B and vertex A, right? So if I can go from A to B, then I can also go from B to A. And if I can't go from A to E, then I also can't go from E to A, right? Because those are always guaranteed to be the same. And therefore, I'm going to get an undirected graph if I have a symmetric matrix. If it's just a general adjacency matrix with ones and zeros all over the place and it's not symmetric, then I have to use a directed graph to represent that, because now it's no longer the case that an edge in one direction implies an edge in the other direction, right? Next one. What if I told you that the matrix, the adjacency matrix of a graph, was block diagonal? Ooh, what would that tell you about the underlying graph? So let's make one here. Let's say I've got a matrix, and we'll label our nodes A, B, C, D, E, and F. And let's say we've got A, B, C, D, E, and F up here. An adjacency matrix normally has zeros on the diagonal. That wouldn't be the case if we allow self loops. Okay, so if we had our F node that was connected to the E node, and we also allowed the F node to connect to itself, then in that case we wouldn't necessarily have zeros on the diagonal. But most of the time we're not going to deal with a matrix a graph like that. We're going to deal with a graph with no self loops here, right? Now, block diagonal, I'm going to make this one go like this. I'm going to say A goes to B and C, but not D. And therefore, I'm going to make this undirected, by the way. And I'm going to make this go 0, 0, 0. And I'm going to say that this is a 0 and a 1, and therefore this is going to be a 0 and a 1, and I'm going to make those zeros, and I'm going to make those zeros. And then I'm going to make D go to C, and C go to D. And then I'm going to say that's 0, and that's 0, and that's 0, and that's 0. And now I'm going to say, let's make D, let's see, we already have A through D, so now we just got to do E and F. So I'm going to say A, B, C, D, and I'm going to put a 1 here and a 1 here. Okay. Now, if you look at this, you will realize this is indeed block diagonal, and that's because I can divide it up like this, and I now have all zeros on the non-diagonal blocks. Okay, so this is indeed block diagonal. Now, can you look at this and tell me anything interesting about this matrix? And in particular, can you tell me anything interesting about what the graph will look like that represents this matrix? So let's draw it here. Let's make our nodes A, B, C, D, E, F. And let's put in all our edges. So A goes to B and C, and that's all. B goes to A and D, that's all. C goes from A to D, and that's all. D goes to B and C, and that's all. E goes to F, and that's all. And F goes to E, and that's all. Okay, so what did we learn here? What we learned is that this is a disconnected or non-connected or unconnected graph. And that is always going to be the case if we have a block diagonal adjacency matrix. And that's because, if you think about it, what I've done is established a subgraph of A through D. And I have guaranteed that I have all zeros between the A to D group and the E to F group. And I also have all zeros down here between the A to D group and the E to F group. So I have inherently forced a division in my vertices into one block of A through D and the other block as E through F. And so I'm going to get one subgraph like this, one subgraph like this, and they are not going to be connected. If I made them connected like this, C to F, say, then I would be going in here and I would say, let's take C to F and make that a 1. And let's go from F to C and make that a 1. And you can see now I've violated the block diagonalness. Okay? So a block diagonal matrix always represents a disconnected graph. Fun fact. Now, you might ask if the converse is true. So let's say I have a disconnected graph. Am I always going to get a block diagonal matrix? And you'll realize if you think it through that it won't always be the case, but it comes down critically to how you chose to order the vertices in your matrix. So our graph just had A through F there, right? And we could have made any of those be the rows and columns. We could have said A, B, C, D, E, F. We could have said F, D, E, C, B, A. We could have said F, A, C, E, D, B, right? It doesn't matter what order we put them in. It's still the matrix represents it. So the moral of the story is that if you have a disconnected matrix, then there is always some permutation of the rows and columns. In other words, there's some sequence you can put them in that will give you a block diagonal matrix. So you can't guarantee that the matrix is always going to be block diagonal just because you have a disconnected graph. But there's a way to reorder the rows and columns such that you will get block diagonal. And that is only true for a disconnected graph. For a connected graph, there's no way to make it block diagonal because you eventually have everything connected to everybody else, which means there's no way to partition the nodes into two or more groups, none of which touch each other. Okay? Interesting. Let's give me another one. What if I told you that the matrix was upper triangular? So clearly we're dealing with a disconnected graph here, right? Because now it's not going to be symmetric for sure. And remember, upper triangular means that everything below the diagonal is going to be zeros. So everything down here is going to be zeros. Only up here could we have non-zeros. This is all zeros down here. So does that tell you anything about the graph? And the answer is yes, and let me give you an example. So I have, we have a curriculum at UMW in the computer science department, and we have the following classes. We have 110, and we have 220. These are programming courses, and 240, that's our object-oriented design course. And we have 340, which is our data structures course. We have 430, which is software engineering. We have 350, which is applications of databases. We have 125, which is discrete math. And we have 414, which is our networking course. Now, we have a lot of other ones besides just these. But let's just make a graph of these. And what I'm going to do is I'm going to put in arrows representing the prerequisites. So if I have some node A and it has an arrow to B, what that means is that A is a prereq for B. For B, which means you have to complete course A and pass it before you can take course B. And here's what the prerequisite arrows look like here. They look this, and this, and this, and this. 220, you need that to take 240. You need 240 to take 340, and you also need 125 to take 340. You need 340 to take that. You need 350 to take that. You need 240 to take that. Okay, so those are the prerequisite arrows. Now, clearly, there are not going to be any cycles in this graph. When I say cycle, what I mean is there's no paths where you can start at a vertex and go from vertex to vertex along the arrows and end up back where you were. There can't be any paths because if so, then it would be impossible to graduate, right? We would basically be milking our students for infinite tuition. Because if there were a cycle, then that would basically be saying, hey, you have to take course 111 before you take course 229, and you have to take course 229 before you can take course 353, and you also need 229 before you can take course 127, and you need course 353 before you can take course 111. In this case, we have a cycle, because right here, 111 to 229 to 353 and back is a cycle. Therefore, this is impossible to graduate with, because you'd never be able to take 110 unless you'd previously had 353. Oh, but you can't have had 353 unless you had 229. Oh, but you can't have had 229 unless you had 111. Oh! So really what we've got here is an infinite loop. We've got a catch-22 that can never be solved. So in something like a prerequisite chain, and by the way, this is same concept applies to all sort of work breakdown structures in project management, where they say, hey, we've got tons of different things we need to take care of before we can complete building this, office building or this house or whatever. So basically they make a list of all the different tasks that different people need to do, and then they draw dependencies between them, right? So we can say, hey, we can't do this part of the house until this and this happens, and we can't do that until this happens. And basically the whole thing can't have any cycles, otherwise it would be impossible to build a house because you couldn't ever get into that cycle because of the chain of dependencies, okay? So that's what a cycle is. And a graph that's directed that doesn't have any cycles, like a real work breakdown structure for a building, or like this prerequisite thing that I just drew, is going to be called a DAG, which stands for Directed Acyclic Graph. A directed acyclic graph is a graph where the edges are directed, they have arrowheads, but where we guarantee there are no cycles. And that way it's possible to complete the project. It is possible to visit all the nodes. It is possible to complete the curriculum and graduate. So, told you all that stuff about DAGs, and now the punchline is, if the graph is a DAG, that is going to go with an upper triangular adjacency matrix. Ooh, weird. Why is that? Well, let's see. So if I go back to this example here, and I make my adjacency matrix. Now again, just like we looked at a moment ago for the disconnected block diagonal thing, it critically depends on the order of the vertices here. And so I'm going to choose a particular order, and you'll see why I do. I'm going to make the order be 110, 125, 220, 240, 340, 350, 414, and 430, barely enough room for that one. Okay, so let's see what we got here. 110 is a prereq for 220, and it's not a prerequisite for anything else. 125, so again, these are also numbered here, right, because an adjacency matrix is square, and we know that every row goes with one vertex, and every column goes with one vertex, so we can just duplicate the row names and the column names here. And so we got that. So now 125 is going to be 0, 0, 0, 0, 1, 0, 1, 0. Make sure you see how I got that based on the graph there. Then this is going to be 0, 0, 0, 1, 0, 0, 1, 0, because 220 is required for 414 and for 240 and nothing else. 240 is going to be 0, 0, 0, 0, 1, 1, 0, 0. 340 is going to be 0, 0, 0, 0, 0, 0, 0, 1. 350 is also going to be 0, 0, 0, 0, 0, 0, 0, 1. 414 is going to be all zeros because it is not a prerequisite for anything. And 430 is also going to be all zeros because it is not a prerequisite for anything. Now, voila, let me declare victory and then explain why it's a victory. We have an upper triangular matrix because everything below the diagonal, if I can get the right thing circled here, is 0. And therefore, this is, in fact, upper triangular as required. Now, to see why that has to be the case, what you have to realize is that in order to complete this curriculum here, there has to be some order in which I can take the classes. There has to be an order, and one such order is 110, and then 220, and then 240, and then 125, and then 350, and then 430, and then 414, and then 340. Now, double check my work here and verify that I could take the classes in this order, which, by the way, is a different order than I have here, right? This order I have 110, then 125. Here I don't take 125 until the fourth class. But in both of those orderings, it is possible to take all of the courses without violating any prerequisite, because you can take all the things that are upstream of arrows before you take the thing downstream. So the idea here is that there is some ordering of the vertices, some permutation of the rows and columns. There may be more than one, in fact, just like there was for the block diagonal thing. There's a lot of different ways you could sort those vertices. In fact, in the block diagonal example, we needed to have A through D first and then E through F, or E through F first and then A through D, but any shuffling of the A through D within itself and any shuffling of the E and F within itself would lead to a block diagonal matrix. Same thing's true here. If I pick some valid ordering where it is possible to get all the classes taken without violating a prerequisite chain, then it must be upper triangular. Because if you think about it, the first class I'm going to take better not have any prerequisites. So it better have a column of all zeros. And then the next class I'm going to take better also have no prerequisites, except maybe that one. The third course I'm going to take better not have any prerequisites, except maybe the first two I've taken. So at each step along this path, there's only a limited number of options that are possibly one. All the rest below the diagonal must be zero, otherwise it wouldn't be a valid ordering in order to take all those courses there. Okay? So, interesting how there's this deep connection between the adjacency matrix of a graph and what its properties are, and then what the graph's properties inherently are. And there's other examples of that too. These are sort of the easiest ones to kind of just give you a flavor for, right? Now, one other thing we can do when we look at this adjacency matrix is we can multiply it by some stuff in order to get some interesting results. So here's sort of a basic one that's not super whiz-bang, but let me put this one graph up that we have. Again, I'm going to say we have A, and I'm going to say we have B, and I'm going to say we have C, and I'm going to say we have D, and I'm going to say we have E. And remember that in this little graph, D could go to E, and B could go to E, and C could go to E. Everybody likes to go to E. B could go to C and back again. A could go to B and back again. A can go directly to C without going through B as an intermediary, and D can go to A. And I believe those were all of our edges on the thing. Now, the adjacency matrix for that, you will recall, was 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, and then all zeros down here. And that was true if we choose the ordering A through E in alphabetical order, right? If we had chosen to number the rows and columns of our adjacency matrix with some other ordering of them, these rows and columns would be shuffled around. But under this ordering, this is what the adjacency matrix is, okay? So let's call this thing ADJ. That's the adjacency matrix. Now, question, what if I take ADJ and I multiply it by a vector, a column vector of all ones? What do I get? So we're going to be taking this column and we're going to be multiplying it, and multiply again means dot product, right? We're going to be dot producting it with this column here, and what are we going to get out? We're going to get out 2. And when we dot product this second row with all ones, we get 3. And when we dot product the third row, we're going to get 2. And the fourth row, we're going to get 2. And the last row, we're going to get 0. What is this? This is the in degree of each vertex, right? Because E has an in degree of 0, and D has an in degree of, I'm sorry, not the in degree, my bad, the out degree. Right, so E has nothing going out of it. D has 2 things going out of it, as does C, as does A, and then B has the biggest out degree, because B has 3 different things going out of it, right? So taking the adjacency matrix, multiplying it by a column of all ones gives you the out degree. And similarly, if I have the adjacency matrix, and I multiply it on the left by a row of all ones, then I'm going to get the in degree. So a row of all ones times this first column gives us 2, and that's because A has an in degree of 2 and an out degree of 2. If we do it for B, we're going to get 2. If we do it for C, we're going to get 2. If we do it for D, we're going to get 0. If we're going to do it with E, we're going to get 3. And again, that's because E has the biggest in degree. That has 3 things coming into it. D has nobody going into him. And A, B, and C all have 2 things. So that gives you the in degree. So a nice little operation there that reduces the question of how many connections does each node have down to a matrix question that can be solved by a matrix multiplication. But that's not all. And one of the things that comes up very often in social networks and other kinds of networks is this question. Who are the most influential vertices in that social network? You might ask yourself the question, hey, if I look at actually Twitter and I see all these different people following each other, which nodes really are the ones that are easiest to spread news from because more people are following them? But it's not just how many people are following them, it's how many people are following the people who are following them, and how many people are following the people who are following the people who are following them, right? So basically, if I was some node in Twitter and I tweeted something that was like a really juicy piece of news, the question is, how fast would people see it? Because anybody who's following me would see it right away in their newsfeed. And then maybe they retweet it or pass it on to their friends. And when they do that, all the people who are following them will be able to see it, etc., etc. So the question of who's the most influential node is not as simple as who has the highest out degree, although that's one very simple way to talk about who has the most influence. But that may not be the whole story, because if I have 10,000 people following me and yet all of them are losers that nobody follows, well, the news isn't going to travel fast from me, right? Because I'm going to announce it, I'm going to tweet it, and then all those 10,000 people will hear it right away, but no one's going to hear it from them because none of them have anybody following them. So to be the truly most influential vertex, I have to look at the graph as a whole, and the linear algebra properties are going to help us get at that. Now, as I said, eigenvalues are the thing that's really going to help us get a solid answer to that question. Overall, who are the most influential nodes in this network, and who in this network is the most the best listening node? So in other words, if I wanted to pick somebody and say, hey, I really want to know what's going on in this network, which vertices have the biggest in degree, and the people who have an in degree from them also have a high in degree, right? So it's the same problem in reverse. Who is the biggest collector of information versus the biggest disseminator of information? Both those things can be cracked by using eigenvalues and eigenvectors, which again, I'm going to make you wait on 2 episodes till we cover that. But one thing we can do just very simply now is a different kind of question, and that is this. Suppose I want to know how many different paths there are from one node to all the other ones of a certain length. And it turns out that's closely related to this other problem of looking at the entire graph and asking who is the most influential node. So if I ask myself, let's say I want to go from A to A. How many paths are there of length 2? And I'm going to call those 2 paths, just for brevity here in our notation. How many 2 paths are there? And you can look at this and eyeball it and say, well, I could go from A to B and back to A. And really, that is our only option, right, is to go from A to B to back to A. So there's going to be one of those. And then I might ask myself the question, how many 2 paths are there from, let's say, B to E? How many paths of length 2 are there from B to E? And if you look at this, you'll realize that I could go from B to C to E. I could also go from, I guess there's only one. There's only one path, or one 2 path from B to E, okay? Now, what if I want to take 3 paths? Let's ask ourselves the question, how many different ways are there to get from B to E in paths of 3 steps? And you realize that I can go from B to A to B to C, so that's one of them, B to A, back to B, back to C. That is a path of length 3. And when I say 3, of course, I mean 3 edges I have traversed, right? Another option is to go from B to C to B to E. So I've got B to C to B to E. And then another one I could do is I could say, let's go from B to A to C to E. B to A to C to E. Now, those are the only 3 I see. Do you see any more? I'll let you answer that. But I'm going to say that, subject to any errors I've made here, there are 3 paths of length 3 from vertex B to vertex E. Okay, so look at that graph and you can kind of figure out, sort of by trial and error, how many different paths there are of a particular length from one vertex to another. Now, question. Is there a way to automate that process? What if I showed you that graph and I said, I want to know how many different paths there are from A to E of 40 or less lengths? Is there any way to figure that out? And you'd be like, man, I would be here all day trying to count up all the different ways I can get from A to E of in paths of length 40 or less. My goodness, I'm going to have to keep track on this huge sheet of paper all the different ways of doing it. And I'm surely going to count some more than once because I'm going to mess up. I'm surely going to miss some. It's a big error-prone process, right? Turns out that we can use a very simple operation to accomplish that, and that is matrix multiplication. So check this out. Suppose I took our adjacency matrix here, which we're calling ADJ, and suppose what I did was multiply it by itself. So I'm going to take ADJ times ADJ. And I'm going to ask you what you're going to get. Now, we know how to do matrix multiplication, so let's just kind of go through this, right? So we're going to take this right here and dot product it with this column, right? Because really, I'm going to put another copy of this matrix over here. 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, and 0, 0, 0, 0, 0, right? So I'm kind of doing that in my head, but if you want to write it out, you can. So let's do that. So we're basically going to take this row dot producted with this column, and that's going to give us, I believe, 1. And we're going to take this top row, and we're going to dot product it with the second column, and that, I believe, is going to also give us 1. And then we're going to take it and dot product it with the third column, and we're also going to get 1. And then we're going to dot product it with the fourth column, and of course we're going to get 0 because that fourth column is all zeros. And then we're going to dot product it with the last column, and I believe that last column is going to end up giving us a 2. So that's the first row of ADJ squared. That's the adjacency matrix squared because it's the adjacency matrix times the adjacency matrix. Okay? If you keep doing this, you will get these numbers, 0, 2, 1, 0, 1, and you will get 1, 0, 1, 0, 1, and you will get 0, 1, 1, 0, 0, and you will again get all zeros on the bottom row. Now, what's the method to the madness here? This is, I kid you not, the number of 2 paths from every vertex to every other. Whoa, are you serious? Yeah, that's what it gives you. And so we said there's one way to get from A to A in a path of length 2, right? And in fact, that's what it gave us right here. And we said there are 2 different ways to get from A to E, because I can go from A to C to E, I can go from A to B to E. Those are the 2 ways to get from A to E in 2 lengths. And that is true for this entire matrix. And in fact, we can repeat this process, because if I take ADJ times ADJ times ADJ, that's ADJ cubed, right? And if you multiply that out, what you will get is the following: 1, 2, 2, 0, 2, 2, 1, 2, 0, 3, 0, 2, 1, 0, 1, 1, 1, 1, 0, 2, and then all zeros on the bottom. This is the number of 3 paths from every vertex to every other. And so from B to E, we said there were 3 different ways, because I could go from B to A to B to E, or I could go from B to C to B to E, or I could go from B to A to C to E. And that right there is those 3 paths. And there is no way to get to E at all from any number of 3 paths there. And if I have the number of 2 paths in this matrix and the number of 3 paths in this matrix, of course, if I wanted to find the number of paths of length of length 3 or less, then what would I do? I would take ADJ plus ADJ squared plus ADJ cubed, right? That's just matrix addition. Because realize that the ADJ matrix by itself is giving me the number of 1 paths. Now, we don't really think of it as a 1 path, but that's really what it is. Because when we say there's a 1 right there, we mean there is 1 way to get from A to B in a path of length 1. And there are 0 ways to get from A to D in a path of length 1. So this matrix by itself gives you the number of 1 paths. If you add that to the matrix that gives you the number of 2 paths, and then add that to the matrix that gives you the number of 3 paths, you get the number of paths of length 3 or fewer, right? So you can do that, and with a computer it's obviously very fast, and you can easily answer the question, how many different paths are there from A to E of length 40 or less? All we have to do is take ADJ plus ADJ squared plus ADJ cubed plus ADJ to the 4th, all the way up to ADJ to the 40th power. Now, to see why that is, let's consider what's really happening here when we do this matrix thing, right? So let's say we've got our adjacency matrix, which again was 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, and 0, 0, 0, 0, 0. Now, this always blew my mind that this works. I'm like, man, how did it like magically figure out that the answer was the number of 3 paths? And like everything in math, it makes sense if you follow it through logically, and let's see why this is happening. So this is ADJ itself. I'm writing it down 2 times, and we're going to multiply it together, right? And here's what I want you to think about. I want you to think about, over here, I'm going to get some answer, right? And this is going to be ADJ squared. Now, let's just pick a couple of these at random. Let's pick that row, and let's pick that column, just for fun, okay? So this is the row corresponding to B, and this is the column corresponding to B. And that is going to produce this entry of the matrix, right? We've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And I'm realizing I shouldn't have chosen B for both of them, so let me change that. Let me not choose B for the second one. Well, my eraser's too big. I'm going to write this back. That's okay. Let's put this back to 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0. Okay. Let's take a different column. Let's take this column here, just so we can see that it is from B to C. Okay, so now we're not talking about that guy anymore. We are instead talking about row 2, column 3. Okay. Now ask yourself the question, what is going to go in that box? And the answer, of course, is this thing dot producted with this thing. So I'm going to blow this up a little bit. 1, 0, 1, 0, 1. That is that guy right there. And then down here is 1, 1, 0, 0, 0. That is that column right there. And we're going to dot product these, which of course means multiplying each one together and adding them up. And obviously we're going to get a 1 here. Now, the reason this works to give you the total number of paths is this. Think about what this row means. This row means that there's one way to get from B to A. There's 0 ways to get from B to B. There's 1 way to get from B to C. There's 0 ways to get from B to D. And there's 1 way to get from B to E in 1 step. So this thing right there is giving you the number of ways to get from B to everything else in 1 step. Now, consider what this thing means. The fact that there's a 1 there, which corresponds to this 1 here, means that there's 1 way to get from A to C in 1 step, right? So this is from A to C. This is from B to C. This is from C back to C. This is from D to C. This is from E to C. And that's how many different ways there are to get in 1 step. It's the number of ways to get from everything else to C in one step. Now ask yourself this. If I want to find a two-path, what needs to be the case? Well, what needs to be the case is I need to get from B to something, and then from that something to C, right? Because a two-path basically means from B to some node, don't know what, to the node C. Well, if you think about that, this is exactly what we're doing. We're taking the number of ways to get from B to A times the number of times whether or not you can get from A to C, and we're adding that to the number of ways to get from B to B times a 1 if we can get from B to C, plus the number of ways to get from B to C times a 1 if we can get from C to C, right on down the line. So this basically is adding up every single one of these red type of things right here. Because I'm only going to add 1 if this bottom thing is a 1. Otherwise, I'm multiplying by 0 and I'm not going to get it. And then up here, this is giving me the number of ways to get from B to everything else in one step. And that is why A squared, or ADJ squared, gives you the number of two paths. And if you take this to the next step, let's say that I'm trying to figure out, how many different ways there are to get in paths of length 40. How many 40 paths are there? Well, that is going to be ADJ to the 40th, which, of course, is ADJ to the 39th times another ADJ, right? So if we multiply ADJ by itself 39 times and then do it one more time, we end up getting ADJ to the 40th time, right? So think about this. I'm going to start with ADJ 39. Maybe this is 17, 455, 36, 0, 92, 75, 418, 419, 6 million, 3, etc. So basically, each one of these tells me how many ways can I go from B to C, say, in exactly 39 steps, right? So this is the number of 39 paths from B to C, from B to D, from A to B, from A to E, all those, it's exactly the same thing, right? So if I multiply this by our adjacency matrix ADJ, right, because this is ADJ to the 39th, and then this is ADJ right here, which is 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, and 0, 0, 0, 0, 0, then I'm doing the same thing. I'm looking at, let's say, this row and this column. And what I'm saying is, if there's 75 ways to get from B to A in 39 different steps, and there is a way to get from A to C in one step, then bada boom, that's another 75 paths of length 40 that go from B to C. Oh, but that's not all, because there's also 418 ways to get from B back to B. And then if I'm on B, sure enough, I can get from B to C. Therefore, there's another 418 paths of length 40 from B to C. So these were through A as the 39th step. And this was through B as the 39th step. And then, since this is 0, this is 0, this is 0, I don't care how many different ways there are to get from B to C in 39 steps, because I can't get from there to to C. And I don't care how many different ways there are to get from B to D in 39 steps, because I can't get from there to C. And I don't care how many different ways there are to get from B to E in 39 steps, because I can't get to C from E. And so the whole thing works out to give you exactly that number of paths. Fascinating thing. Let me just kind of run this in R and in Python just to kind of show you this here as a last thing. So what I've done here is I've made a matrix, and this is the very vector we were looking at just now, or the very matrix rather for that graph. So if I look at A, let me run this thing, and I look at A, it looks like that. So what I've done here is I've said, well, let me make another variable called a.power, because that's going to be our powers, and then make one called a.sum, which is going to be the sum of all of the powers. And then I just have a little loop, right? For I in 2 to 40, because I've already done a of 1. A of 1 was this guy here, right? So I'm going to say, let's multiply a power by a and set that equal to a power again. So that basically is going to make a power be a squared, then a cubed, then a to the fourth, then a to the fifth, etc. And then, after I've done that, I'm just going to add it to the sum, so I have a running total of all of the paths of length 40 or less. And if I run that thing and I say, hey, what is sum? It's going to be this. And so this thing tells me that there are 331,160,280 different ways to go from A to E in 40 steps or fewer. Same thing in Python. If I go to Python here, I've made this little array, which is our adjacency matrix. So let's run that. And if we look at A, we will see that it looks just like the one we had here. We called it ATJ a minute ago, but I'm just using A here because it's a little shorter, right? What I'm doing here is I'm saying let's make a temporary variable called a power and another one called a sum. And I'm going to use a power to basically collect all the powers of a squared, a cubed, a to the fourth, and so forth. And then I'm going to make a sum be the running sum of those powers so that I can get the number of paths of 40 or less. So I'm going to basically go from 1 to 39 here. I don't need to start at 0 because I've already done the first one, right? So basically an additional 39 times, I'm going to say set a power equal to a power dot a. So I'm going to take a squared and then turn that into a cubed and then turn that into a to the fourth and then turn that into a to the fifth and then add up in my sum thing the total running sum. And so I basically added up all the different powers so I can get the number of paths of 40 or less. So if I go here and look at that and say, hey, what is a sum? It turns out it's this. So it looks like I've got 331,160,280 different paths of length 40 or less because I added up all those different powers to get from vertex A to vertex E. And the other ones are similar in that table. Fascinating stuff. And social networking and in general network data, whether you're looking at a network of computers, whether you're looking at a network of genes and how they influence each other, whether you're looking at a network of countries and who has borrowed from who, whether you're looking at a network of computer companies and which ones buy from who or which ones influence who, the ability to analyze that and find deep properties of the graph simply by doing linear algebra operations is a huge burgeoning field that is taking off in the 21st century. And if you're interested in it, I suggest you take a look at that field. Thanks a lot. Good job on episode 7. I will see you next time on All the